How do you guys like the house?
We love it, but is it in our budget?
Yeah, this house is only $11.
Wow, that's $199,989 below our budget.
But I have to warn you, some people say that this house is haunted.
What? Haunted?
Now, legend has it that many years ago, a tiny Japanese baby went insane, killed her entire family, and then disappeared. They say that to this day, she still haunts this house.
We'll take it. Wow, I'm so excited to move in.
I have a bad feeling about this.
Pish posh, those are just rumors. Let's go eat some watermelon.
Okay.
And then I was like, what was that?
Let's go investigate.
Oh no, she's coming towards us!
We're doomed!
Wait a minute. According to the speed ray, our vertical and horizontal change in velocity can be modeled by parametric functions. That means we can use calculus to avoid tofu.
We're doomed.
Look, using this computer program, the horizontal velocity can be modeled with x of t equals 3t squared minus 4t plus 2 inches per second, and her vertical velocity follows the curve y of t equals t sine t inches per second.
So what? That won't tell us where she'll be, only how fast she's going.
But we can integrate the functions to find her vertical and horizontal displacement.
But won't we need an initial condition? How about that, Einstein?
We can eyeball it. Okay, so the integral of the horizontal change in velocity is x of t equals t cubed minus 2t squared plus 2t plus c, which is easy to find using the power rule, but you can't use the power rule for the second one.
So how do we find it?
I'm glad you asked. We can use integration by parts to find that the integral is y of t equals negative t cosine t plus sine t plus c. Now, by evaluating these integrals from 0 to 3, we know where we have to be in 3 seconds.
What about the initial conditions?
Oh, of course. Using the fundamental theorem of calculus part 2, we can find that the horizontal displacement is 15 inches, and the vertical displacement is 3.11111111 inches. So, in 3 seconds, she will be 39 inches away and 24.11111111 inches off the ground.
So we need to not be there.
Right, so in 3 seconds, we need to be there. Oh no, she's coming back to us following a new parametric curve. Now we need to find the new change in velocity and...
Or you just do this. Watermelon?
Sure. Man, this is some great watermelon.
Tell me about it. Again?
Jesse, stop! Watch out for this falling ladder.
Oh my god, if they fall in front of us, we could trip and die. The evil ghost of Sudoku must have put us here. How will we ever get by?
So we can use related rates to figure out how fast the ladders are moving to avoid getting crushed or tripping and dying.
Good idea. The ladder's 13 feet long and it appears to be sliding on the wall at a rate of 1 foot per second.
And the base of the ladder looks to be 5 feet away from the wall, and it also looks to be a right triangle.
We need a formula to relate all these rates. What formula relates the sides of a right triangle?
The Pythagorean theorem, and in this case, x squared plus y squared equals 13.
And now we have to differentiate the formula.
Okay, and the derivative of x squared plus y squared equals 13 is 2x plus 2y equals 0.
No! You forgot to use the chain rule. It's 2x dx dt plus 2y dy dt equals 0.
Oh yeah.
Now we can find dy dt, which is the rate at which the ladder is falling, by plugging in what we know. X is 5 feet, dx dt is 1 foot per second, and y we can find by using the Pythagorean theorem. 5 squared plus y squared equals 13 squared, so y is 12 feet.
So when we plug these numbers into the derivative, we get 2 times 5 times 1 plus 2 times 12 times dy over dt equals 0. Now we have to isolate dy dt, which is the rate at which the ladder is falling.
dy dt is falling at a rate of 5 over 12 feet per second.
This means we have to run under it now!
Avina, you're alive!
But not for long. Look!
Curse you, Coco!
Help me, the shower's filling up!
How long do we have to figure out what to do?
I guess we can use related rates again.
How? I don't see any triangles.
Well, we can use the equation for the volume of the rectangular prism. But wait, that has two variables.
Not if we measure the width and the depth of the shower.
It's 5 feet by 4 feet!
Oh, good. So v equals 20h. And so we can take the derivative of that, which is dv over dt equals 20 dh over dt. But wait, there are two variables.
Not if we know the rate of the volume increase.
It's increasing at 2 inches cubed per second!
So 2 equals 20 dh dt. So dh dt equals 1 over 10 inches per second.
So we can divide Avita's height by the rate to figure out how long she had until she drowns.
I'm 5 feet, which is 60 inches!
So I have 600 seconds, or 10 minutes.
Oh my god, what are we gonna do?
Wait a minute.
Oh no, she's coming. Whoa, that was close. Where's Sabina?
Oh no, Sugeko's still chasing Avina.
We can stop Sadisnos by throwing something at her. But how will we know she wrote she don't mean?
Can we use calculus?
We can use this motion detector to find a function that models spheric movement.
Okay, so what's the function?
The computer is saying m of t equals 16 over 3 to the n plus 1. So for every second for t, she moves m of t. So the limit as t approaches infinity is 0. Wait, this makes no sense.
Since the function is the distance she moves every second, not the total distance traveled, we need to do a summation.
A summation?
Don't worry, series aren't that bad. First, we should see if the series is geometric.
It sure doesn't look like it.
We should simplify to make sure. First, let's divide the constant 16 over 3. Now we have 16 over 3, 1/3 to the nth power, which is geometric.
Okay, so what do we do now?
Now we plug into the sum of a geometric series formula and get 16 over 3 times 1 over 1 minus 1/3.
That simplifies to 8 feet, so she'll stop moving 8 feet away. Okay, so Sagiko will be 8 feet away. But how do we determine how far we need to throw this chair to hit her?
If we throw the chair following the function y equals 0.2x, we can use arc length to find the distance needed to throw the chair to knock out Sayako.
Using the arc length formula, a would be 0 and b would be 8. And we need to find the derivative of y equals 0.2x.
The derivative of that is just 0.2, so we can use the arc length formula.
0.2 squared is just 0.04, and 0.04 plus 1 is 1.04. Now we have L equals the integral from 0 to 8 of the square root of 1.04 dx. Now we can integrate.
The integral of root 1.04 dx is just root 1.04x. Then we can use the balanced computer solution.
The square root of 1.04 times 8 minus the square root of 1.04 times 0 equals 8.158. So we need to throw the chair 8.158 feet.
Avina, watch out!
Is she dead?
I think so.
How do I hide the body?
If we put her on her side, we can find an approximate function of the outline of her body. Then we can find the volume needed to stuff her in a trash bag.
Now I have to measure her to find the bounds of the integral.
Lol, she's only 5 feet. What a baby.
So if we revolve the function around the x-axis, we can then use the disk method.
Wow, you're knowledgeable for a toddler.
Thanks.
If the function y equals sine squared of 5 minus log x relatively models half of Salate's silhouette, we can rotate it about the x-axis to figure out her volume. Then we know how big the trash bag needs to be to fit her. Since she's 5 feet tall, we take the integral from 0 to 5 of sine squared of 5 minus log x dx. We get 5.686 feet cubed. What a baby, she will definitely fit in the trash bag.
Aha! I'm not really a ghost. You're actually on a reality TV show called Keeping Up with the Cadavers. This house is actually a set, so we're gonna have to reclaim it. Thanks for
Darn.
participating.
Wow, you got us good.
That was a good one. Oh, I got mine.
What the f?